Okay, so for the last 2-3, I think we have 3 more classes. Okay, so today's class, Monday's class, and Tuesday's class. So everybody saw my announcement, right? So we're going to have classes on Tuesdays because we have a next Wednesday is a holiday, and the week after that, Wednesday and Friday, there won't be any class because I'm on travel. So we're going to make it up using Tuesdays, and looks like to complete the presentations we need 1 more day. So we will have to come in on a Saturday. Okay, on a Saturday morning for an hour. We can set up the time later. Okay. And so what we're going to do is, for today's class, we'll do today and Monday's class, we'll do wideband amplifiers. Yes.
Sir, when doing the mixer design, I saw the literature where they people talk about IIP2.
Yes.
IIP2 and how to
okay. Sure, we'll talk about it at the end of today's class. Okay, so let's finish up whatever we have today. I'll discuss the project details at the end of the class. Okay. Okay, so what was I saying? So we're going to meet for an hour on one of the Saturdays. And so for today's class and Monday's class, we'll look at wideband amplifiers. We probably won't have a chance to get into too much detail. Maybe for the most basic circuit, we'll go into some detail. But beyond that, we may not have, but it's just to give you a flavor. Okay, because we've been pretty much for the full semester, we've been looking at narrowband circuits. So there are a lot of applications where you need wideband circuits. So we'll look at the case of amplifiers. We'll look at another type. So today we'll look at some general methods, and then on Monday I'm thinking we'll look at a specific kind called the distributed amplifier. Okay, that's also quite interesting. And on Tuesday we'll see if we have some portion left over from these. We'll do it on Tuesday. And then I wanted to cover one class on analog and RF layout. Okay, because all of you said you have not had any course in layout, right? So I thought we'll just cover some of the general techniques. Again, since it's one class, we may or may not be able to cover everything, but we'll try to cover it. Okay, try to cover as much as possible. Okay. So first of all, so what kind of applications will you require wideband amplifiers? So broadband, but what kind of, so for example, if you need to do chip to chip communications, okay, between 2 adjacent chips through a PCB, okay. Okay, other cases, optical fiber communications. For example, you might have some TV circuits. Okay, so the TV bandwidth is quite large. It goes from several tens of megahertz to several hundreds of megahertz. Okay, so that could be another application. Measurement equipment. For example, oscilloscopes. Okay, a lot of these circuits have traditionally been used in very wideband measurement circuits, like for oscilloscopes is a good example. Okay. So another new topic of research in just RF circuits is of traditional RF circuits is UWB, okay, or ultra wideband RF. So it goes all the way from 3 megahertz to around 10 megahertz, almost a 7 gigahertz. Sorry, 3 gigahertz to 10 gigahertz, almost a 7 gigahertz bandwidth. Okay, the idea is you have such a wide bandwidth, you transmit it at such a low rate that you don't interfere with anybody else. So the power spectral density of your transmitted signal should be very less, but your overall signal bandwidth is quite large. Okay, and it's usually used for short range communications. So it is being thought of as, for example, a replacement to USB. So it's USB you have to keep plugging in to the computers. You want to have some kind of wireless protocol for that. Okay. So your circuits need to be operate all the way from 3.1 to 10.6 or something like that. Okay, your circuits need to be able to, so you are transmitting signal throughout that bandwidth. So if you look at your you probably need to have something like this. Okay, you probably need to have something like this, your circuit response. Okay, let's call this the gain, for example. Okay. So first of all, what do we know about, I think you guys must all have studied about gain bandwidth product, right? So if you have a given amplifier with a given load, typically and a given power consumption, your gain bandwidth product is constant. So let's take the case of a common source amplifier. Okay. And what we are going to assume is it's driving an identical amplifier. That's a very good way to characterize the circuit, the bandwidth of the circuit itself. So let's assume that has some capacitance, load capacitance CL. So your voltage gain of your circuit is, in this case, GM RDS over 1 plus SCL RDS. Okay, so it's a single pole amplifier in this case. And omega naught is your omega 3 dB. Okay. Your unity gain frequency omega u is nothing but A naught times omega naught, which is just happens to be GM over CL. Okay. Okay. Now, if you want to design a second amp, so what you know is, given the the amplifier itself, you can operate at multiple points. For example, you can operate on this curve. Okay, you can operate at a lower gain and a wider bandwidth. So that is your gain bandwidth trade-off, right? Now, suppose you want to increase the bandwidth further. What can you do? Assume your load capacitance is fixed. Okay. What can you do? One thing you can do is, of course, increase power dissipation. Okay. But suppose you do that, suppose you just increase the current in the amplifier. What happens? If you plot your GM versus I naught, okay, of course it increases, but eventually it does saturate because you're starting to go into short channel, right? Remember velocity saturation. So eventually your GM is going to saturate as a function of current. So you really don't gain that much. Okay. And of course, if you increase the width, GM increases, but CL also increases. Okay, both increase by the same amount, so your bandwidth will remain constant. Okay, the other thing you can do is cascade a number of amplifiers. Okay, so that way you want to run, so we'll look at it next class. Okay, that is another way to do it, which is you basically cascade. And that lets you get out of this trade-off for a single amplifier. But at the end of the day, now each amplifier is going to have its own delay. So at the end of, if you're cascading n amps, you're going to have n times the delay of each amp. So at the end of the day, what you're actually doing is, so this is your fundamental trade-off in any wideband amplifier. So you're basically trading off gain, bandwidth and delay. Okay. So if you just look at traditional circuits, we tend to think only of gain and bandwidth. But in reality, you can trade off delay to get more gain and more bandwidth. Okay. And next class we'll look at the distributed amplifier, which does do something like that. Today we'll look at the single stage amplifier, which uses some other circuit techniques. Okay. So let's look at some bandwidth enhancement techniques. The simplest one is, so let's say the original amplifier is this. So you have some load resistance R, okay, and you have some load capacitance C, okay. Your initial omega naught is 1 over RC, okay. So now you want to extend this bandwidth, okay. One of the easiest ways is to add an inductor in series with the resistance. Okay. So what you are effectively doing is the inductor adds a 0 to your transfer function. Okay. So what you are effectively doing is the magnitude of the 0 increases as a function of frequency. Okay. So over a small range you are going to use that to improve your gain. Okay. If you look at it in the time domain, what does the inductor do? The inductor doesn't allow the current inside it to change suddenly. So if you are looking, let's say your Vin is a step response. So your step response is a good way to measure the bandwidth of the system. What happens? The inductor tries to keep the current constant, so most of the charging current comes from the capacitor. So if you look at the voltage across the capacitor, which is what you are interested in, it can rise much faster. Okay? So that's what's happening. So what is your gain now? Is nothing but Gm times Zs. Okay? Z of S is the impedance. Let's assume Gm is constant because we know the trade-offs involved in changing the current and size. Okay. Okay. We are going to write it in a particular form, and you will soon see why. Okay. This is the impedance transfer function. So, of course, this has a 0 and it has 2 poles. The poles may be complex conjugate, we don't know that yet. Okay. So, we are going to define the following. Okay. First of all, of course, the original bandwidth is 1 over RC. We are going to define a time constant which is RC. Okay. We are going to define a factor called M. Okay. M is nothing but original time constant, okay, over the new time constant. What is the original time constant? RC over the new time constant added is L over R. So the time constant of the 0. Okay. And note that this is nothing but okay 1 over omega naught tau. Oh, sorry, this is the new time constant. Sorry, tau is the new time constant L over R. Okay, is that clear? So now we can look at the normalized impedance Z of S over R. Okay, which is nothing but S tau plus 1 over. We can again replace the S tau plus 1 over S squared tau square M plus okay. So now we are interested in the magnitude. over yes s square tau squared m plus s tau m plus 1.
In the term you have S square LC, right?
Yes.
LC is 1 by omega naught square.
1 by?
Omega naught square.
No. Remember, this is not a resonant circuit. Omega naught is 1 over RC. Omega naught is the original bandwidth, 3 dB bandwidth. Okay. So these are no longer resonant circuits. Okay. Remember that. So you can't don't imagine omega naught to be 1 over root LC. It is. We are talking about 3 dB bandwidths here. Okay. Plus omega tau m the whole square. No, we are defining the L over R time constant to be tau, that's all. Okay, we are not going to use tau anywhere, it's just to simplify the expression, that's all. But you'll see what we are trying to find out is, we are trying to find out actually the value of L, that's what we are trying to find out, right? We are not trying to find out anything about tau, we are just defining a variable called tau which is in terms of L over R, okay? So what do we know? Let's say the new 3 dB cutoff is omega 3 dB. Okay, we know that this will be 1 over root 2. So you can just take this and equate it to 1 over root 2. Then you okay. So let's simplify the expression. So let us say. Let's say new variable omega tau the whole squared is x. Okay, so what you'll get is 1 plus x over 1 okay. Oh, 1 plus x, sorry, you're right. Okay. Now you can cross multiply and solve this equation. What you'll get is m square x square minus 1 equals 0. So this is what you'll get. Okay, and then now again you can solve this. X equals 2m plus 2 minus m squared plus root of, m is x is nothing but omega tau the whole squared, so you're going to take the positive root. Okay, so same thing squared plus 4m squared, okay, over 2m squared. This is the same thing here. No. So what I did is I took the minus inside this and changed the sign. Okay. So remember, x is omega 3 dB times tau the whole square, which is times okay, omega 3 dB or omega naught the whole square times 1 over m squared. So now you can put this back into the previous equation, into this equation. Okay, you're going to get two roots. You're going to get a second root inside a root, obviously. But let's look at minus m squared by 2 plus m plus 1, okay, plus okay. So you get something like this, okay. It looks crazy, and what you'll see is this is actually the simplest of the bandwidth extensions. Okay, what we are going to do is for the rest of them we're not going to derive anything because it will just take too long. Okay, what I'll give you the results, and you can, what is actually quite easy, instead of trying to solve for trying to maximize this, it may be easy to just plot. Okay, you can plot omega 3 dB or omega naught as a function of m. You can vary m from 0 to whatever and see what happens. Okay, that may be the easiest way. So if you plot it, this is what you get. Okay. So let's call this the bandwidth extension factor, which is this guy, omega 3 dB over omega naught. Okay, if you plot this as a function of m, okay, what you will get is something like this. Okay, you get something like this. Okay, so what you are interested in is this guy, the maximum bandwidth extension. So that happens to be root 2. Okay, m equals root 2 maximizes this function. Okay, so now let us say you put m equals root 2 and look at the gain response. Okay, you need to do that. First of all, before we do that, for m equals root 2, you need to find out what omega 3 dB or omega naught is. This happens to be 1.85. Okay, so in other words, your bandwidth extension factor is now 1.85. Okay, this is actually very good because without increasing power, area of course increase, but not transistor size or anything else, you have managed to almost double your bandwidth. Okay, so this is actually a very powerful method. But now let's see what happens if you plot your AV as a function of let's say AV of omega as a function of omega. Okay, what does your initial gain look like this? Okay, let me initial gain look like this. Now if you plot the new one, okay, so it starts off here at the same DC gain, we know that. Eventually your 0 starts to add some, increase the magnitude response. Okay, and then it goes down. So if the original bandwidth was omega naught, your new bandwidth 3 dB bandwidth is going to be 1.85 omega naught. No, that's what we did, right? The 3 dB, see 3 dB below the DC is what you defined here. Oh sorry, unity gain bandwidth will be the same. Yes, actually let's assume this is not 0. Okay, so let's assume this is not equal to 0. So yeah, at some point in time they will meet, definitely. Okay, yeah, so eventually they will merge. Okay, so you have managed to get an increase in the bandwidth, but now you have a problem. Your magnitude response is actually peaking. Okay, so what that means is you actually have for different frequency components you have different gains. You don't want that. Okay, so it turns out in this case this is almost 20% peaking, so approximately 1.5 dB, 1.5 to 1.6 dB. Okay, so there are a lot of applications where you don't want that. Okay, so what you may want is a maximally flat response for magnitude. Okay, so let's see. So again you can go back and try to find out the value of m that you would need for a maximally flat response. Okay, how do you do that? One easy way to do that is give a constraint that at omega naught, the value of the transfer function should be the same as the DC transfer function. Okay, that is one way to do it. To say no peaking. Actually, I won't even say maximally flat. I'll say no peaking. Okay, that's not necessarily the same as maximally flat. Okay, so let us start off with no peaking first. So no peaking, you can say at omega naught, at the old 3 bandwidth, it should still have the same response as at DC. Okay, so let us say okay. Okay, if you give this condition, this gives you an m equals 2. Okay, and your bandwidth extension factor happens to be 1.8. Okay, which is pretty good. So this one gives you, okay, so what it will give you is, you are only putting the constraint that at omega naught it should be same as DC. You will still observe a little bit of peaking after that. Okay, so you will observe much less peaking. You will observe maybe 3% of peaking, which is much less. Okay. Okay. Next, you want to find out the maximally flat case. Okay. Which means zero peaking, absolutely no peaking at all. So what you'll get is you'll get a value of m that is 1 plus root 2, which is 2.41. Okay, so one way to find out the maximally, put the constraint of maximally flat, you know that, so what you have to do is, there is a standard method, okay, which is make sure the maximize the number of derivatives whose value at DC is 0. That's a very standard way to derive a maximally flat response. Okay, so that gives you this m equals 2.41. So for that, here, sorry, it gives you a bandwidth extension factor of 1.72, which is still pretty good. You have not moved very far away from your optimum. Okay, instead of 1.85, you have 1.72, but your magnitude is pretty flat. Okay. Okay. Now, there are a lot of cases. Okay, so we have looked at the magnitude, but what we have not looked at is the phase. Okay, because a true wideband amplifier has a linear phase. Okay, which means linear phase means you have constant group delay. That is, the delay for every frequency is the same. Okay. Now, this one does not satisfy that condition. Okay, so the phase will be distorted. So if you really have information in the phase, so you will have problems. So for example, so a lot of these amplifiers are used in cases where you have baseband signaling. You don't directly modulate the signal. There are a bunch of ones and zeros. Okay, so there will be cases, so you'll end up with some amount of ISI because of phase distortion. So the fourth condition we are going to put is a maximally flat phase response, rather a maximally flat group delay. Okay, as linear a phase response as possible. Okay, so your group delay is nothing but d phi by d omega, where phi is the phase. Okay. Again, you are going to do similar. So what you are going to do is you are going to maximize the number of derivatives that have a value of 0 at DC. Okay, so if you do this, what you get, so all of these things, there's a lot of algebra behind it, okay, but it's good to know the results. Okay, so you get m equals 3.1. Oops. And you get a bandwidth extension factor of 1.6. Okay. So remember that the conditions for each of these are different. Okay. So depending on the particular application where each one is important, you will need to choose a particular case. For example, once you get a flat group delay, your amplitude response is no longer going to be maximally flat. Okay. You won't have peaking, but it won't be maximally flat. You will have, right, a faster roll off. So if you are asked to design such an amp, okay, the constraints you will have. So what, first of all, what will you be given? You will be given the DC gain, of course. So the application will demand a particular DC gain. You will know your load cap C, irrespective of whether it is driving another amp or not. You know your load cap C. So you know that load cap. Automatically from these two, you know your omega 3 dB. Okay, because from your power constraint, you will have your current, you will have your GM, and then you can find out your R, and then that will lead to your omega 3 dB. Okay. Now you will have to develop the constraint on which kind of optimization you want. Max bandwidth, so you have so you have these three constraints. Okay, so you will choose one of these three depending on whichever one is important. So actually, so sorry, your omega 3 dB is what the bandwidth you need for your signal. It's not necessarily the initial bandwidth. It's what bandwidth you need finally. Okay. So you choose one of these, you'll know omega naught. Okay. So this will give you R. Okay. This will give you your GM, what you need. Okay. Based on the constraint again, you will have M. So L is okay. You can find out L. Now the other thing to remember is, if you go back to your amplifier, okay, unlike your narrowband wireless RF circuits, in this case you actually have an explicit resistance in series with the inductance. In other words, you don't care much about the Q of the inductor. You want the inductance, but you don't care about Q, because already the resistance will be in probably hundreds of ohms. Okay, so you don't care about the Q. What you want to maximize is minimizes die area, which means you want to maximize the amount of inductance for a given area. Okay, so in this case you will be probably using very thin lines for the inductor. Okay, typically thinner lines will give you more inductance, as well as you can minimize the area. Then quite very common is having multi-layer inductors, okay, except not in shunt but in series. Okay, so you'll wind inductor on one layer, you'll go down, okay, wind it in the same direction so that it adds magnetically, and keep doing it. Okay. The only thing you have to care about is self resonance. Okay, not anything else. Okay. But then remember, once you start making thinner and thinner layers, I mean thinner and thinner traces, automatically your self-resonant frequency will go up. Okay. Okay. So very common to use multi-layer inductors. Okay. What are the other methods? So you have a second method called series peaking. Okay. Okay. So instead of adding the inductor in shunt across the load, you are adding it in series with the load. Okay. The basic idea in this is to what you are actually doing is, so let us say let's say the device drain to bulk capacitance is CdB. Okay. So what you are effectively doing is this inductor separates out CdB and C. Okay. So initially the transistor actually sees a very high bandwidth because the capacitance is reduced, and now it's trying to charge only its own CdB. Okay. So the rise time here is very fast, and the inductor for a sudden rise is going to be a very high impedance. Okay, for a step response. Okay. Eventually the inductor also starts conducting, and you will start rising. The signal at the output will also start rising. Okay. So effectively what you have traded off here is actually the delay. Right. Now the output is actually a delayed version of the input. Okay. Okay. So in this case, you can show that your L. So okay. So let's say L again, we'll call it R square C over M. Okay. You can do the calculations again. What you'll find is maximum bandwidth possible comes from M equals 2. Your bandwidth extension factor works out to root 2, which is 1.41. So in other words, this is not as powerful, okay, as shunt peaking, because shunt peaking gives you actually 1.6, 1.7, and the max bandwidth is actually 1.85. Compared to that, 1.4 is just not good enough. You're using the same number of inductors. Okay, so if you had to choose between the two, you'd probably choose the shunt peaking. Okay. Sorry. Not necessarily. So what you'll have to see is you'll have to see how much series resistance. You'll have to work out the details of the impedance. Okay, and then see. Okay, it won't be as important as the what we have seen before for like LNAs and not LNAs, like VCOs for example. But it may be important. Eventually, after a certain point, it will become important. Okay. It so turns out this is also the case for maximally flat amplitude. Okay. Next, your maximally flat group delay. So that happens at M equals 3. And you get a bandwidth extension of approximately 1.36. Okay. So now the next question is, you have looked at shunt peaking, you have looked at series peaking. Why not use both? Because it's not necessary. So both are not mutually exclusive. Okay. So the next kind is called the shunt series peaking. So it is there is no, okay, so it gives you bandwidth extension over the original RC case, okay, but compared to shunt peaking, there is no advantage. In fact, shunt peaking is much better than this. Because if you do shunt series, you can actually get even better, because remember, the way they work as far as the transient step response goes is different. One of them allows more of the shunt current to flow through the load path. The other one separates out the capacitances. You can use both techniques. Okay, so the way they work is different. Okay, so you can definitely use both. Okay. Okay. So we won't go into too many details, but you can get better bandwidth extension factors from this. Okay. Then there are also other methods. Okay. There is a method called shunt double series peaking. Okay. Oh, sorry. Okay, so you can have something like this. Now, if you look at this circuit, you can actually replace L1, L2, L3 by a pair of magnetically coupled inductors. If you look at the equivalent circuit, it will turn out to be the same. Okay, so that you have some coupling factor K, okay, and let's make them equal for now. Okay, so you can get something like this. Also, what is very common in many of these circuits, if we go back, so let's say we go back to the shunt. Sorry, give me a minute. Okay, what you can also do is, it's very common to add a bridging capacitor. It's called a bridging capacitor because bridging across the inductor. Okay, what happens is there will be some resonance between L and CB that actually also helps to boost the bandwidth. Okay, and you can find conditions on CB value, on L value, and for the same conditions we put in before, right? Maximum bandwidth extension, maximally flat, and so on. And so similarly, yes. Sorry? That I think it's too much for this class. Okay, to explain why that happens maybe a little bit too much. Okay, but we'll just assume that it does help. Okay. So you can put a capacitance CB across this. So this structure is called the bridged T-coil. Okay, very popular. It's a very popular technique for bandwidth extension. Okay, you can see this one is called a T-coil and it's bridged with a capacitance C. Okay, and now you can find condition on K because the coupling factor is another parameter. Okay, so what you will find is you can show that CB is C by 4 times 1 minus K over 1 plus K, where K is your coupling factor. Your L is assume that both are equal. Okay, it turns out to be R square C over 2 into 1 plus K. Okay, so now you can again find out. So these happen to be the most optimum cases for C and L. But now with this optimum value, you can sweep K and find out what is the best. Yes, maximum bandwidth, but assuming K has a certain value, okay, for a fixed K. Then what you do is start varying K, okay. Turns out K equals half, okay, gives you group delay. Okay. K equals 1/3 gives you the Butterworth response. That's a maximally flat amplitude. Okay, and of course, most importantly, let's just call it your bandwidth extension factor. Okay, now you see why it is very popular. In the other cases, we looked at 1.6, 1.5, 1.8. You can get almost 2.8, which is almost 3 times the original bandwidth. Okay, this is like huge. Just by adding a pair of coupled inductors and some capacitance. Okay, and then the other kind of variation on this is you can have asymmetrical T coils. We assume that L's are equal. You can have asymmetrics. You can have L1 and L2 that can give you a different amount of bandwidth extension. Okay, so I think as far as wideband amplifiers go for today's class, we'll stop here. On Monday's class, we'll look at distributed amplifiers. Okay, yes, you had a question on the mixer.
What is IIP2?
Okay, IIP2. So remember, as far as for IIP3, we defined, you plot the fundamental power against each other. Okay, now you can plot the second order intermod. What is the second order intermod? This is the second order intermod. Remember, if you have a second order nonlinearity, you are going to have omega 1 plus or minus omega 2 terms.
For a mixer, this is the desired sequence, omega 1 minus omega 2.
Not always. Okay, you have to be careful. For a mixer, no. This is okay. So this is omega RF, this is omega LO. But what we are talking about is omega 1, omega 2 here. Remember, we model the mixer as something like this. Remember, there is a transconductance and then followed by the real mixing, which is the switches. So this one is the one which has nonlinearity. This one we don't care, it is just a switch. We modeled it as the signum function, right? So most of the nonlinearity actually comes from the transconductance. Okay, so if you put in 2 tones, at the output here you are going to get omega 1 plus or minus omega 2 and that will get mixed down. Okay, now so similarly you can actually plot your IM2 power, okay, and that will have a slope of 2 and the point where it meets happens to be your IIP2.
So what is the first term?
This is output power versus input power, right?
Output power of mixing.
Output power here of the mixer.
What is the input power?
One of them is either one, right? Both of them have equal amplitudes, remember?
Yeah, but what is omega 1? Like you have 3 frequencies, omega RF, omega 1, omega 2, right?
Either one, right? Because if you put in 2 components, omega 1, omega 2, you are going to get the fundamental gain times omega 1 and omega 2. So it doesn't matter which one you choose. Okay, of course the circuit is going to be symmetric. If you given 2 components of equal amplitudes, it will be symmetric because they are so close. Okay, so now you can plot your IIP2 Now the reason this is important, in a normal, I guess a heterodyne system, we saw that we are interested in IIP3 because your 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1 fall directly very close to your signal, right? And then they get mixed down. In this case, your IM2 components can actually fall because now you are looking at a direct conversion receiver, okay, in the project. So now you are interested in DC. So your omega 1 minus omega 2 term will matter, okay. And what you will see is, since you are all discussing differential circuits, ideally your IIP2 will be infinite, okay. Ideally, if you have differential circuits, because you don't have any even order components, so at the end of the day your IIP2 will be limited by your mismatch, okay. That's why I said in the project assume a 1% mismatch, right? So you will see IIP3 numbers we saw were like what, minus 5 dBm and plus 5 dBm, right? Whereas IIP2 numbers will be 40 plus 40 dBm or plus 50 dBm, something like that.
The project really good actually.
Well, I think if you design any normal circuit, it will be very easy to meet that spec. Okay, I think I have given what, 40 dB, 40 dBm, right? 40 dBm should be very easy with a 1% mismatch. Okay, that shouldn't be a problem. If anybody has a problem, let me know, but I don't think there should be a problem. Okay. Okay, so we'll stop here and continue on Monday. Okay. Now about the projects, sorry, the paper presentations. What happened? I heard